In projectile motion, it makes a great deal of sense to work in the vertical and horizontal directions because gravity acts vertically, and in the absence of drag, the acceleration is vertical. The point is that the horizontal and vertical components of motion can be treated separately, with the horizontal part at constant speed, in the absence of other forces such as drag, and the vertical motion accelerated by gravity. This is a really powerful tool. To see this point graphically, here's an object launched with an initial velocity v0 at an angle theta to the horizontal. We can resolve this initial velocity into a horizontal component and a vertical component. The object accelerates vertically and it follows a parabolic path like this. A time t later, the horizontal component of the velocity has not changed, but the vertical component of velocity has been reduced by an amount equal to the acceleration multiplied by the time t. Before the top of the motion, that corresponds to a deceleration. Beyond the top of the motion, such as the point shown in the diagram, the velocity is reduced so much that it is now negative. In other words, it is now travelling downwards. We can now recombine the components of the velocity vector to find the velocity at any time t, and the magnitude of that vector is the object's speed. To recap, we saw how the individual velocity components evolve over time, and then we recombined them at the end. In contrast, for the inclined plane, an object on a slope, the horizontal and vertical directions are not the most easy to use. Let's see why by considering the three forces on this object on a slope of angle theta to the horizontal. The weight acts vertically, sure, but the other two forces do not. The reaction force from the surface acts perpendicular to that surface, and the friction acts up the slope, in other words, parallel to the surface. This suggests that parallel and perpendicular to the slope might be easier directions to work with than the horizontal and vertical, so we'll have to resolve the weight into components along those directions. The first trick is to find the angle between the weight and the slope. By considering the angles in the various right-angled triangles in this diagram, it can be shown that the weight is at an angle theta to the slope. We won't prove this here because it isn't the main point of the exercise, but you can try it if you like. Then the component mg sine theta tends to accelerate the object down the slope. If the object remains still, it's because there's enough friction available to balance the mg sine theta force. And the component mg cos theta is balanced by the reaction force. If you make the slope steeper, theta increases. Mg sine theta increases so that there's a greater force accelerating the object down the slope. But mg cos theta decreases, which means that the reaction force decreases. Now it's an empirical law that the amount of friction is proportional to the reaction, so increasing the angle causes the object to start moving through two effects, a greater accelerating force and a reduction in the friction available to prevent it moving. So to summarise, we've seen in two situations how calculations can be made easier by choosing suitable directions in which to resolve vectors into their components.